organizers of this conference for the opportunity to come here and present some of the results that, you're again taking pictures here, oh my god. Some of the results that I was thinking about with my friends. So as you can see, the title is Quantum Critical Transport and NDA-CFT. That is slightly different from what was announced. I did this because I thought of organizing this seminar, this talk, not as a research seminar compressed in time by a factor of 2, but rather trying to give you some purely qualitative ideas and motivations behind our work. So I will be reporting on something that I did in collaboration with Chris Herzog, who must be somewhere in this room here, and Sean Hartman must be also somewhere in this room, well, somewhere. Subir Sajdev is a condensed matter theorist from Harvard, and Demson is at the Institute of Nuclear Theory in Seattle. And these are some of the papers that contain the relevant references. So this talk will be about applied string theory or applied M theory. So what do I mean by that? By that I mean an attempt to use NDA-CFT correspondence as a tool to understand various properties of strongly interacting field theories. And of course, the goal of this is to apply all this formalism somehow to the real world. So for the purposes of this talk, I will focus on field theories that live in 3+1 or 2+1 dimensions. And for simplicity, and also because it is a string theory conference, I will be thinking about relativistic field theories as opposed to non-relativistic field theories. And one example that was, of course, very extensively studied in NDA-CFT is N=4 super-Young-Mills theory in 3+1 dimensions plus various deformations. However, of course, we all know that there is no real physical system whose fundamental degrees of freedom are described by NDA-CFT or its cousins. So does this mean that it is a totally meaningless endeavor to think about this kind of applied NDA-CFT correspondence? Well, in my opinion, the answer is no. And one can take two views on the subject. One view would be to try to construct more realistic models in the context of NDA-CFT, which would involve various modifications to the background geometry, adding probe brains, the ADS-QCD program, and so on. And talks that we heard today in the morning session were along this line. However, today I would like to advocate a slightly different view. That is, instead of trying to come up with more and more refined models, one can try to look for universal properties of strongly interacting gauge theories that would hold in a wide range of examples. And since we are aiming at something universal here, it is plausible that one has a better chance to find something universal if you are looking at finite temperature, because at finite temperature, the details of the ground state will not be so important. So the analogy that I would like to make here is if you think about a classical two-dimensional Ising model. Well, classical two-dimensional Ising model does not describe real ferromagnets, just like N=4 super-Young-Mills does not describe real QCD. Still, the exact solution of the two-dimensional Ising model proved to be very useful in statistical mechanics and was a precursor of the whole field of critical phenomena and universality. And universality is often associated with conformal symmetry. So let's see where different CFTs come up. So if you think about three-dimensional Euclidean CFTs, they show up in classical critical phenomena. So this picture here shows a typical phase diagram for some substance such as water over there. So that's an experimental demonstration in the plane of pressure and temperature. So there are typically three phases: solid phase, liquid phase, and the gas phase. And it so happens that the line of phase transition that separates the liquid phase from the gas phase ends somewhere in the middle of this phase diagram. And the point where it ends is called a critical point, which is characterized by the divergence of the correlation length C here. And for water, it happens to be at temperatures 374 degrees Celsius and pressure about 200 times the atmospheric pressure. So the point I'm trying to make here is that if you look at static correlations in the vicinity of liquid-gas critical point, they are described by three-dimensional Euclidean CFT. And for water and many other liquids, the CFT actually happens to be in the universality class of the Ising model. Now let's think about Lorentzian CFTs. Now Lorentzian CFTs are associated with phase transitions that are driven by quantum fluctuations rather than thermal fluctuations. So what I mean is that if you take some quantum mechanical system at zero temperature, it may so happen that it has a phase transition, a second order phase transition, at some critical value of the coupling constant. In such a case, the dynamics precisely at this critical point will be described by Lorentzian CFTs, and this critical point will have divergent correlation lengths as coupling approaches the critical coupling. So what happens if you now try to introduce temperature? Well, what happens is that now we have two scales in the system. One scale is the correlation length away from the critical point, and the other scale is the scale which is set by the temperature. So if you are somewhere in this phase diagram, in this green shaded region, where the correlation length is so large that it's still larger than the inverse temperature, then the dynamics in this shaded region will be characterized by a Lorentzian CFT at finite temperature. This is in theory. Now, are there any experimental realizations of that? Well, it actually happens that experiments come from the field of atomic physics. And there was much effort recently in engineering, for example, Bose-Hubbard model on optical lattices. So it so happens that if you look at the Bose-Hubbard model at a certain range, at a certain point in the parameter space, then it has a quantum critical point that is described by Wilson-Fisher fixed point. And the system can be experimentally realized with cold atoms and optical lattices. And there was a KTP workshop a couple of months ago, and also a KTP conference dedicated precisely to this subject. So if you think about atomic physics, don't think about atomic physics as some, lowly kind of, field of science, down to earth, low energy, blah, blah, blah. So what atomic physicists do, they actually study three-dimensional, four-dimensional Lorentzian CFTs at finite temperature. And this is precisely the object that we are interested in DSCFT correspondence. Now, can strongly interacting Lorentzian CFTs be relevant to particle physics? Well, naively the answer is no, because the only strongly interacting sector of the standard model is QCD, and QCD is not a conformal field theory. Well, however, remember that we are looking at finite temperature here. So let's look at what latest data tells us about QCD thermodynamics at finite temperature. So this picture shows energy density in QCD divided by T to the 4 as a function of T over Tc, where Tc is the crossover temperature to the deconfined phase for various flavor content. So the point that you should take from this graph is that these lines are very flat, they're very horizontal. So what this means is that energy density is proportional to T to the 4, which is precisely the scaling that you would expect from a conformal field theory. Moreover, if you now look not at energy density divided by T to the 4, but at energy density divided by energy density in the free theory, which they call E. Stefan Boltzmann, then you find that all these lines, for different flavors, they're pretty much close to each other at about 0.8, which is again, this horizontal shape is perfectly consistent with conformal symmetry. Now, so you ask, what happens in some of the conformal field theories that we study in ADS-CFT, such as n equal 4 super-Young-Mills? So what happens in n equal 4 super-Young-Mills is that. So there is a black line here, which is located at 0.75, which is 3/4, the famous mismatch found from analyzing black brain thermodynamics between strongly interacting super young males and free super young males. And of course, if I were completely honest here, I would also show you the graphs for pressure, not only energy density. So pressure does not exhibit such conformal scaling very well, but the deviations are small. At about 2 TC, they're around 20–25%, and then they go down. So the point that I'm trying to make is that thermodynamics of QCD is reasonably consistent with CFT at about 2 to 5 TC, and since this TC is around 170 MeV, you're still in the strongly coupled regime. So I'd like to make one speculation here. Is there a physical reason why QCD at finite temperature exhibits such conformal scaling? So the speculation comes from looking at the phase diagram of QCD in the temperature and pressure plane. So imagine that, okay, so this is the phase diagram. So this is the vacuum phase, quark-gluon plasma, various, color superconducting and CFT phases here. So imagine that, this transition, well, what I drew was first order, but imagine this transition was second order. In this case, you can argue that there is the whole region in the QCD phase diagram, which is controlled by quantum critical point, located here. And if the regime of validity of this quantum critical point extends all the way to this quark-gluon plasma region, well, you can say it is not so crazy to assume that the conformal scaling as QCD is due to some physics of a quantum phase transition. Well, this was just a speculation, but I thought it would be curious to mention. Okay, so the bottom line is, first, strongly interacting CFTs in 2+1, 3+1 dimensions at finite temperature are not, or maybe not so far removed from the real world. And second point is that it makes sense to look for universal properties of real-time response. And once you're looking for universal properties of real-time response, not Euclidean theory, you are led to study transport. Now, what kind of transport is there? Well, there is several kinds of transport. One kind of transport is the transport of momentum, which is controlled by conservation of energy momentum plus viscosities. And there is a universal result for shear viscosity, which says that the ratio of shear viscosity to density of entropy is always equal to 1/4 pi in all ADS-CFT examples that are described by supergravity. And this was discussed extensively in a talk by Andrei Staronets 2 years ago at the Strings conference. There are other kinds of transport. Charge transport controlled by conductivity, heat transport controlled by thermal conductivity. However, if you do calculations, what you find is that conductivity, electrical and thermal conductivity, they're not universal in ADS-CFT. So one may ask, are there other universalities in real-time response besides this eta over S equal to 1/4 pi? And since these naive transport coefficients are not universal themselves, if there is any universality, it has to be more subtle. So this led us to consider frequency-dependent conductivity, not just DC conductivity, which is the limit frequency goes to 0, but the full-blown frequency-dependent conductivity, which you measure by applying some RF field to your sample. And of course, conductivities are related to current-current correlation functions. So at finite temperature, two-point current-current correlation function has two independent, if you wish, rotation covariant index structures, pi t, pi l. So this is the transverse self-energy, longitudinal self-energy. Transverse and longitudinal are with respect to spatial momentum. These two functions are completely independent, pi t and pi l, except when k is equal to 0, because at k equal to 0, there is no difference between transverse and longitudinal. And then Kubo formula from linear response just tells us that sigma of omega is equal to 1/omega times imaginary part of pi t. Okay, so how does this sigma of omega typically look like? Well, that's how it typically looks like in a free theory. So it blows up as omega goes to 0 because DC conductivity is infinite simply because you have free particles. As omega goes to infinity, it approaches some dimensionless constant by dimensional counting in 2+1 dimensions. So what happens in a weakly interacting theory? So in a weakly interacting theory, the singularity at the origin now becomes smoothed out. So this conductivity is large. It's proportional to the mean free path of quasi-particle excitations. And the high-frequency conductivity is again some dimensionless number with some small corrections. And the physics of these two regimes is quite different. So people call this regime hydrodynamic or collision-dominated. People call this regime zero temperature or coherent transport. So what happens in a typical strongly interacting field theory? So in a typical strongly interacting field theory, what happens is this. That's kind of the reason why condensed matter people are interested in ADS-CFT, because ADS-CFT provides toy models where transport can be studied analytically at strong coupling. So just to emphasize once again, the DC limit omega goes to 0 does not commute with the limit of temperature goes to 0. So DC conductivity is finite temperature is given by this intercept here. DC conductivity at 0 temperature is given by this value here. So I wrote here a quote from Subir Sajdev's book on quantum phase transitions, which says, the distinct physical interpretation of sigma of infinity and sigma of 0 make it clear that in general there is no reason for them to have equal values. And then he adds in parentheses, we cannot of course rule out the existence of exotic models or symmetries that may cause these two to be equal. So what I will argue in a second is that these exotic models that Subir referred to is actually M theory. So as you can see, M theory was anticipated in condensed matter community. So the simplest model you can study in 2+1 dimensional. So it's a CFT on a stack of n M2 brains. It's described by supergravity on ADS4 times S7. Thermal state corresponds to a black hole in ADS4. Global SO8 symmetry corresponds to isometries of the 7th sphere, and conserved currents correspond to gauge fields in ADS4. And since this theory has SO8 global symmetry, the two-point correlation function of conserved currents is proportional to the identity matrix in group space. And therefore, if you just want to extract the C mu, it suffices to look at abelian gauge fields in ADS4. And this abelian gauge field, this obey the equations of motion, which simply comes from this Maxwell's action in the background of a black hole in ADS4. So what you find is the following. So you need to solve Maxwell's equations on a background of ADS4 plus black hole. Now, CFT currents, they live in 2+1 dimensions. Dual ADS4 gauge fields, they live in 3+1 dimensions. Now, whenever you have abelian gauge fields that live in 3+1 dimensions, there is electric-magnetic duality, which exchanges electric and magnetic fields. And if you work out the details of what this duality implies for correlation functions at finite temperature, then you find that this pi t transverse self-energy and longitudinal self-energy happen to be inversely proportional to each other and are related by this formula. And now, if you take k goes to 0, this means you want to look at uniform fluctuations. So what you see is pi t is equal to pi l. Therefore, pi is equal to I times omega, and then Kuba formula tells you that conductivity is imaginary part of pi divided by omega. So we find that conductivity is constant. It's just some number for all frequencies. So it happens to be frequency independent. So that's one of the major points that I wanted to deliver here, is that electric-magnetic duality of the dual 3+1 dimensional theory implies omega independent conductivity in 2+1 dimensional CFT at finite temperature. So some comments here. This relation is a very non-trivial relation at finite temperature. So a priori there is no reason to expect any relation between pi t and pi l at finite momentum. Now, if you have never seen this relation before, it's not surprising, because there are no other examples besides ADS-CFT where this relation holds. However, if you assume that ADS-CFT works as it is supposed to work, then there is a large class of, exotic 2+1 dimensional CFTs where we have this relation. And basically, these are field theories which is defined as whatever field theory is dual to ADS4 that has a Maxwell field propagating on this background. well, asymptotically AdS4 that has some Maxwell field propagating on this background. So the point here is that the relation pi t times pi l is equal to constant times omega squared minus k squared should be viewed as another example of universality in AdS-CFT, similar to eta over s is equal to 1 over 4 pi. Now, of course, this example is only supposed to work for, this universality is only supposed to work for field theories that live in 2+1 dimensions. Okay, we can do a little bit, we can go a little bit further. We can study transport in external magnetic field as long as we are interested of applying this whole formalism to condensed matter physics. So what happens if you put your theory in put your two-dimensional field theory in external background magnetic field that is perpendicular to this plane? So what you find is that conductivity now becomes a tensor with non-zero off-diagonal entries. So this is nothing else than Hall effect. And of course, what we computed earlier was the diagonal conductivity, sigma xx. Now, it so happens that in a relativistic theory, the whole conductivity is fixed by boost invariance. So, and the argument is very simple. So, you have your equilibrium state here that has some background charge density rho, some magnetic field, and in equilibrium there is no current, there is some magnetic field, and there is no electric field. Now, imagine you perform an infinitesimal boost. So what happens is that now you have a current which is equal to rho times V, magnetic field is still the same, but electric field is minus V cross B. Now you take this V, substitute it for the current, and lo and behold, you find that sigma xy is simply equal to rho over B, and sigma xx is equal to 0. Now, so this is kind of very, very simple argument. So does AdS-CFT know about the Hall effect? Can one use the, the formalism of linear response, Huber formula, and so on to reproduce this physics? And sure, one can. So for that, we need background charge density in CFT, which means we need to study electrically charged black holes in AdS4. We need background magnetic field in CFT. This happens to correspond to magnetic charge of the black hole. So we need to solve Maxwell equation in 3+1 dimensional bulk with both electric and magnetic charges. And so what you find is that you find something that exactly agrees with basically the kinematic argument, whole conductivity is equal to rho over B. Again, note that the DC limit omega goes to 0 does not commute with the limit B goes to 0. This is because without magnetic field, what we found earlier was sigma xx was finite, but sigma xy was 0. And one can go even further, study the full-blown frequency-dependent conductivity, study Nernst effect, which is basically the electric field, the transverse electric field induced by thermal gradient. And if you are interested in details, you can look it up in these papers. So I would like to conclude with some challenges for applied AdS-CFT correspondence. So the first question that is on this list is how close are AdS-CFT models to QCD or some other condensed matter system quantitatively? Because it's an important problem to know the quantitative answer. One can write down a whole bunch of models in AdS-CFT and calculate various properties, but are we really sure that what is computed is going to be, say, within 10% of the real QCD, 20% of the real QCD, 30% of the real QCD? There must be a way to tell quantitatively how close this is going to be to QCD. And of course, this problem is hard, but it's also important. Another problem is, something that David Mateos mentioned earlier today, is how to study fermions at finite density. Well, this is because before you try to reproduce some new physics with AdS-CFT, you better reproduce some old physics with AdS-CFT. And old physics includes physics such as basic Fermi surface. And the problem here is you need to get rid of scalars, because in the simplest example, when you introduce chemical potential for R charge or chemical potential for the D3, D7 system, you have both scalars and fermions that are charged. So the ground state is not going to be the Fermi sphere. So the question here is, where is where is the thermosphere in ADS-CFT. So another question here is, how do we write down models that describe disorder? So what I have in mind here is quantum Hall effect, where disorder is essential to conductance quantization. And you can also recall that Hall conductivity in this context was given by rho over B, and electric and magnetic charges of the black holes are quantized. And so maybe is this charge quantization of black hole relevant to the description of quantum Hall effect? I don't know, that's just a speculation. So another question is about the nonlinear dynamics, which I guess also something that was mentioned by David earlier today. Basically, so far, most of the effort in this applied ADS-CFT at finite temperature was devoted to study linear response. Now, linear response is something that you can directly read off for correlation functions. Now, if you study something like convective transport, shock waves, then you need to study the full-blown nonlinear Navier-Stokes equations. How do you derive Navier-Stokes equations, not just, the correlation functions that describe infinitesimal fluctuations? How do you derive the full-blown Navier-Stokes equations from the dual gravity? Well, this would be interesting. This is also hard. My final comment here is that in the context of landscape, if you try to connect this somehow to landscape, then in flux compactification, there is a landscape of ADS-4 vacuum. Now, if you believe that every ADS-4 compactification gives rise to a three-dimensional field theory, this means that there is a landscape of universality classes. This means there is a landscape of critical points. So this means that if you want to find something that is related to the real world in the landscape, you should not be looking at the DS4 compactification, because there is only one point in the DS4 landscape that is relevant to the real world, which is the universe. But instead, you should be looking at ADS4 compactification, because there are many critical points in condensed matter which are relevant to the real world. So, and if you're lucky, maybe you can even find, critical Ising models in the landscape. So my conclusion is this: ADS-CFT has been arguably useful in application to strongly interacting QCD matter and trick collisions. Now, can it be useful in application to condensed matter? So one example that comes to mind: so if you perform transport measurement at some quantum critical point and find that pi t times pi l is equal to constant times this momentum squared, then you say, bingo, we have found M theory in the lab. That's it. Thank you.
Edward?
In your diagram where you've speculated that QCD had the zero temperature critical point, what was mu on the horizontal axis? Was it the baryonic
chemical potential?
But that's pretty small at RIC, isn't it?
Pretty small compared to what?
Well, compared to lambda QCD. No.
There are actually two, in the conventional view of the QCD phase diagram, there are actually two lines of this phase transition. One corresponds to the transition, I didn't show the second line here. So one corresponds to the transition from vacuum to nuclear matter. This is probably the one that has small value of the critical of the chemical potential that you have in mind. And the other that corresponds to the transition from the nuclear matter to the color superconducting phase. And that one is of order lambda QCD.
Any other question or comment? Well, if not, let's thank our speaker again.